All right, our next distribution is called the Poisson distribution. It's a very important and widely used distribution and has a very specific motivation and intuition behind it. So the Poisson distribution is a distribution that we get, let's see here. I lost count, I think, yeah, we're on 7. So this is 6. So the Poisson distribution has a very specific motivation behind it. Let's lead by an example. So an illustration is, how do we model the number of deaths to occur on a given day? So a single day. Okay. So let's think about a situation in which number of people, the population is large. And let's suppose that each person dies independently with some small probability. So, of course, this is not really accurate. People do not die independent. People do not die independently. And people do not all die with the same probability, but that's going to be our assumptions. So in this case, if X is the number of deaths, then X is a binomial. The number of deaths is binomial NP. It's the sum of the number of individual independent events, all with the same probability. Those are Bernoulli random variables. For each person, it's either a 1 if they died and 0 otherwise. So then we know then that we've already calculated this. Expectation of X is N times P. And what can we say about the probability of X equal to K? Well, the probability that X is equal to K, we know, is N choose K, P to the K, 1 minus P to the N minus K. It's the binomial probability mass function. And if we write this, we expand this out a little bit. So N choose K is N fall K over K factorial. Let's do this. N fall K over K factorial. Okay. P to the K, I'm going to put an extra N in here. I'm going to say N times P to the K. In order to make that work, I have to take N to the K on the bottom. So I'm multiplying by 1 effectively. And then let me just split this out. It's 1 minus P to the N, 1 minus P to the minus K. Okay. And let me rewrite this a little bit. 1 over K factorial times N fall K over N to the K, N to the K, N P to the K, 1 minus P to the N, 1 minus P to the minus K. And now what we want to assume is, for large values, for very small values of P, and the mean mu, which is n times P, is, let's say, of moderate size. So the average number of people who die on a given day might be 2. But if there's 1 million people in a city, P is very, very small. So what can we do with that? Well, what we can do with that is to realize that if we take log of 1 minus P to the power n, so now we're going to use some properties of logs. If we have, and there's 2 really important properties of logs that I'll write down. Log of a to the power n is equal to n of n times log of a. And log of a times b is log of a plus log of b. So this is equal to log n log 1 minus p. For very small values of p, log of 1 minus p is like minus p. So this is approximately minus np, which is equal to minus mu. So that means that we can write, for small values of n, for small values of p, large values of n, 1 minus p to the n is approximately e to the minus mu. So to rewrite this, we realize, okay, this is 1 over k factorial. This is like 1 because n falling factorial k is similar to n to the power k for large n. N times p is actually mu to the k. 1 minus p to the n, that's like e to the minus mu. And 1 minus p to the minus k, that's like 1 because p is small. And so it's 1 minus something really small. It's like 1 minus 0 to a power. And so if you put this all together, what we're left with is mu to the k, e to the minus mu over k factorial. And this is an approximation, right? This is how we derive an approximation in the case where p is small, n is large, n times p is moderate. But this is where we actually derive the Poisson distribution. So the Poisson distribution, X has the Poisson, so X has Poisson distribution with parameter mu if the mass function of X is equal to mu to the k e to the minus mu over k factorial for all non-negative integers. And in this case, we write X is distributed as poi of mu. So now with this, this is a case. So where does the Poisson distribution come from? It comes from modeling rare events. So the Poisson distribution is common for rare events. Why? Well, because as we saw, the deaths example that we have up here is modeling rare events. How many rare events occur in a large population? And if we have that, then yes, we can potentially model that by binomial, but we get a much simpler closed form expression and approximation through the Poisson distribution. So we think of that as a Poisson random variable. The Poisson distribution is amenable to factorial moments calculations. So the factorial moments of the Poisson distribution, how do we calculate them? Well, suppose x is Poisson with parameter mu, then the factorial moment, expectation of x falling factorial k, is sum over all possible values of x, right? So of n fall k, mu to the k, e to the minus mu over k factorial. And what's important to notice about this, no, not mu to k, mu to the n, right, is that this can be rewritten as n equals j to infinity, e to the minus mu, mu to the n over n minus j factorial. Since we're going from j to infinity, we can actually pull a mu to the power j out, get n equals 0 to infinity. Well, let me change the index to m. M equals 0 to infinity, e to the minus mu, mu to the m over m factorial. But now, why have I done all that? Because what this now looks like is this is just the Poisson mu PMF over all possible values. So the factorial moment, why is there a J here? What am I doing? Sorry about this. I switched from K to J at some point. The K factorial moment of the Poisson is just the mean, the first moment, to the power K. They're just powers of the first moment. So that allows us to very easily calculate expectation of x. The expectation of x, that's the first moment. It's the first factorial moment. And the variance, which we calculated above, in terms of factorial moments, we saw that the variance can be expressed as second factorial moment plus first minus first squared. So second plus first minus the first squared. So that's actually also just equal to the first moment. The mode, so some other properties, the mode of the Poisson, the most likely value. So the mode, the most probable value of Poisson is the smallest integer, the largest integer smaller than mu, the floor of mu if mu is not an integer. And it's both mu and mu minus 1 if mu is an integer. And how do we see this? Consider the fact that the ratios of the probability of x equal to k divided by the probability that x is equal to k plus k minus 1 equal, well, it's mu to the k, e to the minus mu over k factorial, mu to the k minus 1, e to the minus mu over k minus 1 factorial. So this is equal to mu over k. And so what's happening then is that we want to see, well, what's the most likely value? And we just see how these are either above 1 or below 1, right? So these are either going to be above, for what values are these above 1? And then at what point do they turn to be below 1? And when they turn to be below 1, we see that these actually is multimodal or is unimodal. It goes up. And then once it goes below 1, that means the probabilities are decreasing. Okay. For J, in the positive integers, we know that the probability that is at least J is at most mu to the J over J factorial. And therefore, well, how do we see this? Well, how do we see this? Well, probability that x is greater than J is K equals J to infinity. Mu to the K, just the sum of the probability masses. We can pull a factor out, mu to the J, e to the minus mu over J factorial, and then leave each term in, and we get 1 plus mu over J plus 1 plus mu squared over J plus 1 times J plus 2, etc. And what's the key idea? The key idea now is that this here is strictly less than mu to the J e to the minus mu over J factorial times 1 plus mu over 1 factorial plus mu squared over 2 factorial and so on, because J is at least 0. But this is exactly the Taylor expansion for e to the mu. And so that's going to cancel with this other e to the mu, and we get mu to the J over J factorial. So that's just a way that we can potentially approximate or give a bound on probabilities. It's to give you an idea of how we can, potentially these are useful techniques to be able to manipulate probabilities in a particular distribution. Okay, so those are the basics for Poisson, where it comes from. It's a model for rare events. Sometimes it's called the law of rare events, is that if you have a binomial with large n, small p, so that n times p is a moderate value, we can use the Poisson to approximate the binomial. And that actually is what's going to lead us to the next section, which is on what's called the law of rare events. We've calculated the mean, the factorial moments, and we've seen that the structure of this distribution is very amenable to calculation. And the law of rare events is really where the Poisson distribution finds itself being used in practice, or being used a lot in practice and sometimes in theory as well. So we'll talk about that next.